So I'm going to kind of build on what Nicolas and Powell talked about. So, but I'm going to take it a little bit further, talking about storing memories in neural networks, in particular how single neuron activation function is going to change the stories of calculations that people do. So, as I think Powell mentioned, that the way that neural networks usually learn, or people think neural networks learn, are through changes in synaptic plasticity, and these are both about learning in brain neural networks, real neural networks, and in artificial neural networks. And but there is there are differences, of course, between how synaptic changes happen in the real neural network, in the cortex perhaps, and in artificial neural networks. So in the brain, in the real brain, it's usually synaptic plasticity mechanisms like the long-term potentiation or long-term depression. In artificial neural networks, it's usually iterative algorithms, for instance, those based on backpropagation. And there is I think a kind of conceptual difference between the two, that in the case of the brain, synaptic plasticities, LTP and LTD, are largely dependent on pre and post synaptic activity patterns. So they don't really depend, or at least a leading order, they don't depend on third neurons or fourth neurons or the whole network. Whereas in artificial neural networks, the way things are trained, for instance, in the simplest case of a feed-forward network that you're trying to use for categorization, you show a number of examples. There's an output. The output probably in the beginning is not what you want, so you calculate the error between the output and the desired output. And there's an algorithm of backpropagation where you backpropagate the error, and then based on that, you change the weights between neurons inside the network or in the hidden layers. So in some sense, the first one, the brain algorithms for learning or changing synaptic weights, is very simple, kind of self-organized mechanism that depends locally on the pre and post-synaptic firing patterns. Whereas in the artificial neural networks, it's a more complex a way of iteratively changing the weights until you get the desired output. And this is, at least for a long time, has been thought to be non-biologically plausible, this kind of artificial algorithms, although there have been attempts, and I'll talk about them. But there has been kind of a general consensus that this kind of non-local iterative algorithms that are used in artificial neural networks are much more powerful or efficient than the local biologically plausible ones, like the Hebbian learning and all the other variants of it. There have been, this consensus is so strong that people have even been proposing and suggesting that backpropagation can be, or actually is, implemented in the brain. This is one example from 2020 where Jeff Hinton, one of the founders of backpropagation and artificial neural networks, have been trying to argue that, despite all the difficulties or complexities that backpropagation has, that they can, I just quote here, argue that feedback connections may instead induce neural activities whose differences can be used to locally approximate these signals and hence drive effective learning in deep networks in the brain. So the argument usually goes as follows, that these learning non-local algorithms like backpropagation are very powerful compared to local ones. Hence, they should be implemented in the brain because the brain is good, and therefore we have to find ways to argue that they are implemented. And but what about this consensus? I personally don't particularly follow this kind of logic, but but even the starting point of whether these algorithms, the AI algorithms, are more efficient or powerful than local biological plausible ones, where does it come from? Well, it comes from a lot of theoretical work and numerical experimentations that people have done. But in this talk, what I want to kind of reflect on is that one has to be more careful with making this kind of statements, and they have to be quantified, and you'll see that in certain contexts that they are not necessarily valid. So for that, I'll focus on re-evaluating this consensus, and I'll talk about the case of attractor neural networks. So Nicolas and then Powell explained the kind of concept of heavy cell assemblies and the Hopfield model. So originally, probably the idea was of cell assemblies was proposed by Hebb. It was kind of made mathematically. The mathematical formulation was kind of developed by John Hopfield, and then it was analyzed by Denny Amit and other people ever since, which attracted a lot of people from statistical physics to analyze this kind of systems. So there is a huge literature on these kind of networks, and I just briefly mentioned what Powell already said, that the main idea is that there is a network in the brain. There's kind of some object producing some activity in the brain that leads to synaptic plasticity. So neurons that are that fire together, wire together, here shown with this kind of different color of synaptic weights. And next time you see a partial object, part of the previous object, so you activate a part of the network, you'll get the whole network and the full activity retrieved. So that's essentially the idea proposed by Hebb. And then the question that statistical physicists and other people were interested was how many patterns can be stored and successfully retrieved in a network like this. Because as you increase the number of kind of objects that you want to store, gradually the patterns will start overlapping with each other, and those overlaps lead to noise or errors in retrieval. You want to retrieve something, you retrieve the other thing. And that's when your attractor neural network does not function as you wish. And this question, the way you answer this question is usually like this. So initially it was answered for neural networks with binary units. Just some notation. So suppose that you have a network that has n units, neurons. Each unit is connected to C number of modifiable connections, and each of those modifiable connections is shown by Jij, which is the weight from neuron J to neuron I. Okay, so that's just these three numbers that are important. And then this is kind of like what Nicolas was talking, just describing the architecture of the network. And then you have to decide about single neuron model. So again, initially the calculations and analysis were done on binary units. So the state of the neuron, which I'm noting with VI, is the state of neuron I. It's a binary variable. It's either +1 or -1. It is determined through a sign function of the sum of the input that it receives from the other units. And if that input is above 0, then the output is +1, otherwise it's -1. Okay, so this is just a standard Hopfield model. In the standard Hopfield model, actually, this C is equal to n-1. So every neuron is connected to every other neuron, but it doesn't have to be. There are other versions. The memories that you want to store look like this. They're P patterns, let's say, and each of those patterns is shown by eta mu. So it's just a vector of eta 1 mu, eta 2 mu, and so on. So these are randomly generated IID numbers, +1 and -1 again. There's P of them, and essentially the distribution of each of these P etas here is a double delta function on a +1 and a -1 with weight 1/2 and plus, and sorry, with probability 1/2 it's +1, with probability 1/2 it's -1. And the Hebbian learning rule is just, it's in its simplest form, is that neurons that are co-active or co-inactive, or they have the same activity level in the same pattern, they increase their weights, otherwise they decrease. Okay, so that's basically the learning rule that Hopfield considered for this for this system. Now, in the original version of Hopfield, the fully connected Hopfield model, where C is equal to n-1, number of connections per unit is just the number of units itself, and these numbers go to infinity. What you can show is that the capacity, the number of patterns you can store, it's defined as P, the number of patterns divided by the number of neurons, has a critical value that's 0.14. That's the number of patterns you can store and successfully retrieved per unit. Same year as Annette et al. Analyzed this network, Derrida, Gardner, and Zippelius analyzed the highly diluted version of this. The highly diluted version means that each unit is connected to a small going to zero fraction of other units, okay? While both these numbers are large, number of units in the network and the number of connections per unit are large, the ratio goes to zero. In this case, the capacity is much larger. You can calculate the capacity in this time. Now you have to define it basically as number of patterns divided by the number of connections per unit. And it turns out to be 2 divided by pi. That's what these people showed. Okay, so these are like kind of two extremes. Probably this one is much more the diluted version is much more similar to the real brain than the fully connected, and you can see that the capacities are different. The question is this good? So these are all with Hebbian learning, assuming that the patterns are stored with this local simple Hebbian learning rule that Hopfield considered. Gardner, this lady who did very brilliant work during her short life, answered this question. Basically, she showed that the optimal capacity, that is the number of patterns you can, in principle, if you don't restrict yourself to a particular learning rule, can store in the pattern, is actually 2. And that is 14 times that of the fully connected Hopfield model, and 3 times that of the diluted model, okay? So it seems that this one is way higher, and Hebbian learning, which is the way these 2 numbers were calculated, 14 and 3, is highly inefficient compared to what could be done. And another interesting thing is that this capacity of 2 can be achieved actually by backpropagation. Okay, this sounds like a very good argument for saying that the local Hebbian learning rule is not a very good learning rule. It's not very efficient compared to, let's say, backpropagation. Okay. Now, all this was done for binary networks. This is neurons that are binary. They're +1 or -1. That's the 2 states that they can express, and the patterns that were stored were also binary. The neurons and all what I said, that is this kind of inefficiency of the Hebbian learning compared to backpropagation for these attractor neural networks, was a consequence, was done for or shown for binary networks, but neurons are not binary. And in some sense, I mean, I just have to clarify one thing, which is binary, neurons are binary in the sense that they either spike or don't spike. But in this context, the binariness is either high firing rate or low firing rate. So a neuron being in the up state doesn't mean that it's spiking or not spiking. It just means that it's a high firing rate or low firing rate. So in this sense, We know that neurons don't have two levels of activity, but they have a continuum of activity levels that they can express. So a simple yet more biologically plausible neuron model is what in neuroscience probably it's called threshold linear transfer function, and in the machine learning literature they call it ReLU, or rectified linear unit. And that one, everything is the same. As I said, the architecture is the same. It's the number of units is n, number of connections, modifiable connections per unit is c. The JIJs are again the weights between neuron J and neuron I. VI is the state of the unit, but this VI or the state of the unit is not now anymore a +1 and -1, but it can take values, every value above 0. So it's more like a firing rate, okay? And the way it is determined is that it is determined by this transfer function. So if the net input that the neuron receives is below threshold, the neuron does not fire. Otherwise, it fires, and its firing rate increases linearly with a gain function G with the input, okay? So it's, of course, single neurons in the brain are much more complicated devices than this, but this is certainly better than the binary network that we just looked at. The rest is kind of the same. We have patterns that are stored in the network. There is P of them. But now these variables, these etas, that is the activity of unit 1 in pattern mu, unit 2 in pattern mu, they don't have to be binary because the neurons are not binary. The patterns can also be non-binary. And that gives us another degree of freedom, which is kind of going to change the story actually quite significantly. And again, we have Hebbian learning, but now that we can, these kind of patterns that we can store are not necessarily binary, we can choose the distribution from which they are drawn. We have a lot of freedom in that. Remember, in the binary case, these etas were IIDs, and they could only be there could be +1 or -1. That's the only possibilities you had because the neurons could only be +1 and -1. In this case, however, since your neurons are not binary, so you can take firing rate values that are above 0, you can also have patterns that are non-binary. Of course, they can be binary, but they don't have to. So we can choose different distributions for eta for the patterns that we are storing. Of course, it can be binary, like the previous case. It can be ternary, it can be quaternary, it can be exponential. It can be all sorts of distributions that you can assume with a support on the positive real values. And it turns out that for analyzing this network, I need to define two parameters for kind of describing these distributions. One of them is, I'll denote them by F, which is the fraction of active units. That's basically all the weight that is on the non-zero part of this distribution, and a sparsity, which is defined as the second moment divided by the first moment squared of these distributions. For any of these distributions, we can associate to them these two numbers. And it turns out in capacity calculations that I'm going to talk about, these are important parameters. Now, I'm not going to show this. I mean, I can show you the way these things are calculated in general. The approach that Gardner actually proposed is that you want to store a number of patterns in a neuron in a network. So what you really want to do, what really this boils down to, is that you have a bunch of inputs that the neuron is receiving in network from the other neurons, and you want to have a desired output. And the job is to calculate, if you want to calculate optimal capacity for this network, which is how many patterns in general you can store, is to calculate the volume of space in the J space, that given the inputs, we get the desired output. And there are statistical mechanics tricks that one can use for doing this. And I'm not going to go into those, but they are very well written and nicely explained in Elizabeth Gardner's papers. But once you do that, what you can get is Gardner bound or Gardner capacity, or this optimal capacity, compared to Hebbian learning capacity, this time not for the binary network of Hopfill, but for threshold linear networks. Okay, we're just focusing on the highly diluted regime here. That is when the number of units per, the number of connections per unit is much smaller than the size of the network, because that is perhaps more biologically, closer to the biological reality than the fully connected version. And everything in between is very difficult to calculate. So, but I think that the important point here is that if you look at the figure on the left, where I'm plotting the critical capacity versus the fraction of active units in the patterns that we're trying to store in the network. For the threshold linear network, the Gardner bound is the full curve. Okay, so it decays with the number if you increase the number of active units in your in the patterns. Now, the Hebbian network is that if you try to store these patterns with Hebbian learning, the results will depend on what was the distribution from which the patterns were drawn. If the distributions were, if the patterns were binary, then, and you were storing them, trying to store them in a threshold linear network, this would be the capacity versus the fraction of active units. And as you can see, there is a large gap between Gardner bound and the binary patterns. This is pretty similar to the case of Hopfill network. But the story changes. For instance, if you try to store ternary patterns through Hebbian learning in this kind of threshold linear networks, you see that the capacity actually gets very close to the Gardner bound. And in fact, for the quaternary, it even surpasses it, which is a bit strange, because Gardner bound is the optimal bound. But they'll tell you in a minute why that happens. But the key point here is that as opposed to the networks of binary units and binary patterns, where Gardner bound was much higher than the Hebbian learning, here, because you can store your patterns you can generate patterns with different distributions. For some of those distributions, you can actually be very close or even surpass the Gardner bound. So Hebbian learning is extremely efficient in this case, but for these distributions, not for binary distributions, but for these quaternary or ternary distributions. And the way this happens, and the way it may even surpass the Gardner bound, the Hebbian capacity can surpass the Gardner bound, is through sparsification of the pattern during retrieval. So it turns out to be the case, which is shown on this figure, by showing the sparsity of the retrieved pattern divided by the sparsity of the stored pattern, is that patterns become, you store a certain pattern at a given sparsity. During retrieval, the network that has learned those patterns with Hebbian learning will retrieve them with a degree of error, but that error is not kind of random error. It's an error towards the sparsification of the pattern. So it just sparsifies the stored patterns, retrieves the version of it that's sparser, but by doing that, it will gain a very high capacity. There's a number of patterns that you can store is much higher, and that's shown here that that for the quaternary, you can see that that this ratio is very small as opposed to the Hebbian. So So this is what a kind of simulation example of this phenomena. So on the x-axis is the value of the activity or the firing rate of neurons in the stored pattern, and this on the y-axis you have the activity of the unit when the pattern was retrieved. So what you can see, if it was a perfect retrieval, all these dots will be on the diagonal. But what you can see is that the ones that the units that have lower activity in the stored pattern, their activity is pushed to zero during retrieval. So they're just set to zero. Whereas those other ones that have higher activity levels in the stored pattern, they have a correlation with the retrieved value that the network confers on them. Okay, so it is in some sense, it's a very smart trick that Hebbian learning manages to implement. That saves a lot of synaptic resources. The way it does it is that in order for a pattern, in order for a neuron to be inactive, the only condition is that the sum input that it receives is below threshold. For that reason, if the network decides that neurons that are just slightly above threshold or a little bit active, but not too much, if it decides to put them to zero, it can save a lot of synaptic resources because the only condition on them is that this sum is below threshold. They don't have to, the network doesn't have to set all these JIJ's values to have the right output level. And this is exactly what is happening, that these neurons that have a low activity level in the stored pattern are pushed to zero, and the resources that are left, that is the synaptic resources that are freed in that sense, they will be used for storing more patterns through adjusting the active or highly active units.
Yasser.
Yes.
How much time do you need from this point?
One
what?
1 hour. No, sorry. No, I need 2-3 minutes.
Okay, good.
So I just want to show this empirical data that we got neurons from anterior part of the superior temporal circus of rhesus monkeys watching familiar natural scene movies. The recordings, you can fit a distribution to their activity or probability distribution of their firing, and it's usually a kind of an exponential with a peak at zero, and the result is that essentially you are in a regime that about the network can reach about 50 to 80% of the optimal capacity with this kind of the distributions that we have empirically got from monkeys. Of course, this is this is just one data set. Probably for other data sets you would get slightly different numbers. But the point is that the distribution of the activity combined, the non-binary distribution of the activity combined with Hebbian learning appears to be actually quite efficient when it goes to when one deals with storage capacity. So this is the summary here, and well, I mean, the take-home message really is that this kind of the perceived inefficiency of local biologically plausible learning rules is an artifact of studying biologically implausible model neurons and distributions. So it seems that Hebbian learning is actually quite efficient for the task that the brain is facing, that is fast and self-organized kind of learning of patterns, allowing a certain degree of error, but it appears very inefficient if you try to learn binary patterns in binary networks and retrieve them. In that case, yes, Hebbian learning is not efficient compared to backpropagation, but the changing of the single neuron that is going from binary units to threshold linear units, and the change of the distribution of the patterns that are using going from binary patterns to patterns that look more like the activity pattern in the brain. There's kind of this exponential tail of the distribution, makes quite a substantial difference. And in the same line, there is a new paper that my former PhD student Nicola Bulso and me published in neural computation, where we studied the effect of transfer functions. This time not on the for real neural networks or the real brain neural network, but this time for restricted Boltzmann machines. And you can see that in that case also quite substantial differences in the expressibility or the power of the restricted Boltzmann machine can be observed depending on what single neuron transfer function you actually use. And that's it. Thank you.